A linked list is a dynamic data structure that is made up of nodes arranged in sequential form. Dynamic data structure means that we can allocate the required memory while the program is running. So a dynamic data structure can expand or shrink easily during runtime. Unlike arrays, data in a linked list is not stored in contiguous memory locations. When compared to arrays, insertion and deletion of elements is easier in linked lists, as there is no need to reallocate or reorganize the whole list structure. In arrays, insertion and deletion involves shifting of elements, while in linked lists, there is no physical movement of data while inserting or deleting elements. We can use linked lists to implement abstract data types like lists, stacks, or queues. Now, two disadvantages of linked lists are that efficient random access is not possible and some extra memory is required for the implementation. There are different variants of linked lists. In this course, we'll study about these 4 variants, out of which the single linked list is the simplest one. So we'll start with single linked lists. A single linked list is made up of nodes where each node has 2 parts, the info part and the link part. The info part contains the actual data that has to be stored in the list, and this link part is a reference to the next node of the list. This is an example of a single linked list with 4 nodes. The info part contains an integer value. This can be of any other type also. The link part of each node is a reference to the next node. So the link part of this node refers to this node. Link part of this node refers to this node. Link part of this node refers to this node. Now this is the last node, so its link part is null. We maintain a spatial reference variable that always refers to the first node of the list. We have named it start. This reference is the identity of the list, and with the help of this reference only, we can access all the elements of the list. For an empty list, this start will be null. Now let's see how we can implement a single linked list. This is the class node that represents a node of a single linked list. This variable info represents the actual data that has to be stored in the list. We have taken it to be of type int. It can be of any other type also. This link is of type node and it always refers to the next node of the list. This is the one argument constructor. Info is initialized with I and link is initialized to null. Now this is our single linked list class. Here we have this variable start that always refers to the first node of the list. In this constructor, we have initialized the start to null. In the next few lectures, we'll develop all the methods of this single linked list class. Now this is the class demo in which we have this method main, and inside this main we'll test our single linked list class. Here we have created a new single linked list object, and with the help of this method create list, we are creating a single linked list. And then inside this while loop, we are performing various operations on the list with the help of all the methods of the single linked list class. In this while loop, first we are displaying all the options, and then depending on the choice entered, we call a particular method. We have used switch case for this purpose. So in different cases, we have called different methods. Now in the next few lectures, we'll see how to develop and test all these methods of the single linked list class. In this video, we'll see how to traverse a linked list. Traversal means visiting each node exactly once. So we'll start from the first node and visit each node till the last node. Before studying traversal, let us see how we can move a reference forward in a linked list. Suppose we have a reference P that refers to this node, and we write this statement P equal to P link. Now P link refers to this node. So if we assign P link to P, then P starts referring to this node. So writing this statement P equal to P link makes P refer to the next node of the list. Now we'll see how we can traverse our linked list. We have to start from the first node. So we'll take a reference P that refers to the first node. To make P refer to the first node, we'll initialize it with start because start refers to the first node. Now while visiting each node, we'll print the contents of the node. Now we write this statement. P info is 10. So 10 will be printed. Next we write P equal to P link. So now P refers to this node. Now we write this statement. Now P info is 20. So 20 will be printed. Next we write P equal to P link. So P now refers to this node. Now when we write this statement, 30 will be printed. Next we write P equal to P link. So P now refers to this node. And when we write this statement, 40 will be printed. Next we write P equal to P link. P now refers to this node. And this time 50 will be printed. Next we write P equal to P link. Now P will become null. And so we can stop because we have reached the end of the list. We can see that we are repeating the same statements again and again. So we can write this in a loop. And the terminating condition for that loop would be when P becomes null. So this is the loop. P is initialized with start. And this loop continues till P is not null. So this loop will terminate when P becomes null. In each iteration, we are printing the value of P info and we are moving P forward by assigning P link to P. So this is how we can traverse a list starting from the first node till the last node. We can use the same loop to count the number of nodes in the list. Here we have taken a variable n and initialized it to 0. And whenever we visit a node, we increment the value of this n. So when this loop terminates, the value of n gives us the number of nodes in the list. Now we'll see how we can use this loop to search for an element in the list. Suppose we have to search for an element x in the list. Now whenever we visit a node, we'll check info of that node. And if info of that node is equal to x, then this break is executed and we come out of this loop. We have taken this variable position and initialized it to 1 and we increment it each time when we visit a node. So when this loop terminates and x is found, the value of this variable position will give us the position of the node that contains value x. Now this loop can terminate in two conditions. One, when x is found and break is executed. Another, when x is not present in the list and we reach the end of the list and P becomes null. So after this loop terminates, if P is null, it will mean that x is not present in the list. Otherwise, value of this variable position will give us the position of the node that contains x. Now let us see the methods for displaying a list, counting number of nodes and searching for an element in the list. This is a method display list that displays all the elements of the list. If the list is empty, then we'll print this message and return. Otherwise, we'll display all the elements of the list starting from the first element till the last element. Now this is the method count nodes that displays the number of nodes in the list. If you want, you can return the value of n from this method. Now this method search will return true if the element x is present in the list, otherwise it will return false. Now let's come to our main. We have called these methods in cases 1, 2 and 3. Now let's run this program. First we choose option 1. So the list is displayed. Next we choose option 2. The number of nodes in the list is equal to 5. Next we choose option 3. We search for element 2. The element 2 is present at position 2. Next we search for element 45. 45 is not found in the list. Before studying insertion in a linked list, let's see how we can move in a linked list and find references to some particular nodes. In this video, we'll see how to find reference to the last node of the list, reference to second last node, reference to a node with a particular info, reference to predecessor of a node with particular info, and reference to a node at a particular position. So first let's see how we can find reference to the last node of the list. This is the last node, so we need a reference to this node. This is the code that will give us reference to the last node of the list. While traversing the list, we had seen that the loop condition was p is not equal to null. So there the loop stopped when p became null. Now here the loop condition is p link is not equal to null. So here the loop will stop when p link becomes null, and p link will become null when p refers to the last node of the list, because link part of last node is null. So when this loop stops, p will refer to the last node of the list. So this is how we can find reference to the last node of the list. Now let's see how we can find reference to the second last node of the list. This is the second last node, so we need a reference to this node. This is the code that will give us reference to the second last node. Now here the loop condition is p link is not equal to null. So this loop will stop when p link becomes equal to null, and p link will become equal to null when p will refer to the second last node of the list. Because when p refers to the second last node of the list, p link will refer to this last node and p link will be null. So when this loop stops, p will refer to the second last node of the list. Now we'll see how we can find reference to a node with a particular info. Suppose we are given this value x and we have to find reference to a node that contains this value x. If the value of x is 30, then in this list we have to find reference to this node. This is the code that will give us reference to a node that contains value x. We have already seen this code while we were learning searching in a linked list. So this loop will stop when p refers to the node that contains x. And if x is not present in the list, then p will be null. Now we'll see how we can find reference to predecessor of a node with particular info. Suppose we are given this value x and we have to find reference to predecessor of the node that contains x. If value of x is 30, then in this list we have to find reference to this node, because this is the node that contains 30 and this is the predecessor of this node. This is the code that will give us reference to predecessor of the node that contains x. Here inside the loop we are checking p link info instead of p info, and the loop condition here is p link is not equal to null. So this loop will stop when p refers to the last node, because when p refers to the last node, we don't want these statements to work. Now let's see how this code works. Initially p refers to the first node of the list. Now p link is not equal to null, so we check p link info. P link info is 20, it is not equal to x. So break is not executed and p is moved forward. Now p link is not equal to null, so again we check p link info. Now p link info is 30, so p link info is equal to x. So now this break statement is executed and this loop terminates. So we can see that when this loop terminates, p refers to the node that is the predecessor of the node that contains value x. Now let's see how we can find reference to a node at a particular position. These are the positions of the nodes in this list. Suppose we are given a value k and we have to find reference to a node that is at kth position in the list. So if the value of k is 3, then in this list we have to find reference to this node. This is the code that will give us reference to the kth node of the list. Let's see how this code works. Initially p refers to the first node and I is equal to 1. Now I is less than k and p is not equal to null, so p is moved forward and I is incremented. Now again I is less than k and p is not equal to null, so p is moved forward and I is incremented. Now I is not less than k, so this loop terminates. So we can see that when this loop terminates, p refers to the node that is at kth position in the list. This condition p is not equal to null we have placed to terminate the loop in the case when there is no kth position in the list. That is, the number of nodes is less than k. For example, if k is 10 and there are only 5 nodes in the list, then this condition p is not equal to null will terminate this loop. In this video, we'll see how we can insert a new node in a single linked list. These are the different cases of insertion. We'll see all the cases one by one. To insert a new node, we'll allocate a node and make this reference temp refer to that node. This is the node class constructor. So this data will be used to initialize the info part and the link part will be initialized to null. Now first let's see how we can insert a new node in the beginning of the list. We allocate a new node, make this reference temp refer to this node. Now after insertion, this node will be the first node. So start should refer to this node and this node will become the second node of the list. So the link of this node should refer to this node. So first we make link of this node refer to this node. We write temp length is equal to start because this node is referred by start. Next we change start and make it refer to this node. So we write start is equal to temp. So these are the two statements that we need to write for inserting a new node in the beginning of the list. Now the order of these two statements is important. Let's see what happens if we change their order. Now first we write start is equal to temp. So start refers to this node. Now we can see that the link to this part of the list is broken. And now if we write temp link is equal to start, this node will refer to itself. And whenever we process the linked list, we'll be stuck in an infinite loop. So this is the correct way of inserting a new node in the beginning of the list. Now let's see how we can insert a new node in an empty list. For an empty list, start is null. We allocate this new node. Now this node will be the first node of the list. So start should refer to this node. So we just have to write start is equal to temp and this new node will be inserted in the empty list. Now let's see how we can insert a new node at the end of the list. For this we need a reference to the last node of the list. We've already seen how we can find reference to the last node of the list. After finding this reference, we allocate this new node. Now link part of this node should refer to this node. So we write plink is equal to temp and so this new node is inserted at the end of the list. Now let's see the code for all these insertions in our program. This is the method for inserting a new node in the beginning of the list. Here we are allocating a new node. Then we are writing these statements temp link equal to start and start equal to temp. This method will also work when we have to insert a new node in an empty list. Because for an empty list, start will be null. So we'll have temp link equal to null and start equal to temp. Now this is the method insert at end and it will insert a new node at the end of the list. If the list is empty, we'll make start refer to the new node and we'll just return. Otherwise, we'll find reference to the last node of the list. Then we'll write plink equal to temp, where this p is a reference to the last node of the list. Now in this method create list, we'll create a new list. Here we are entering the number of nodes and here we are inserting all the nodes with the help of this method insert at end that we have just seen. Now let's come to our main. We have called this method create list in the beginning of the program and we have called these methods insert in beginning and insert at end in cases 4 and 5. Now let's run this program. Now we'll insert a new node in the beginning of the list. So this new node is inserted in the beginning of the list. Now this new node is inserted at the end of the list. Now we'll see how we can insert a new node between two nodes of a list. Suppose we have to insert a new node between these two nodes. For that we'll need a reference to this node. We allocate a new node. Now for this node to come in between these two nodes, the link part of this node should refer to this node and the link part of this node should refer to this node. So first we'll make link part of this node refer to this node we'll write temp link is equal to p link, and then we'll make link part of this node refer to this node. So we'll write p link is equal to temp. So these are the two statements that we need to write to insert this new node in between these two nodes. Now the order of these two statements is important. Let's see what happens if we change their order. Suppose first we write p link is equal to temp. We can see that the link to this part of the list is broken. And now if we write temp link is equal to p link, then this node will start referring to itself. So this is the correct way to insert a new node in between two nodes of the list. Now we'll see how we can insert a new node after a given node, how we can insert a new node before a given node, and how we can insert a new node at a given position. These two statements of insertion will be the same in all three cases. The only difference will be in how we find this reference p. First, let's see how we can insert a new node after a given node. Suppose we are given a value x and we have to insert a new node after the node that contains x. If x is 56, then in this list we have to insert a new node after this node. That means we have to insert a new node between these two nodes. And for that we need a reference to this node. We have already seen how we can find a reference to a node that contains value x. After finding this reference, we'll allocate a new node and insert it here in between these two nodes by writing these two statements of insertion. So this is how we can insert a new node after a given node. Now let's see how we can insert a new node before a given node. Suppose we are given this value x and we have to insert a new node before the node that contains x. If x is 45, then in this list we have to insert a new node before this node. That means we have to insert a new node between these two nodes. And for that we need a reference to this node. So if we have to insert a new node before a node that has value x, we need a reference to the predecessor of the node that contains x. We have already seen how we can find this reference. This code will give us a reference to the predecessor of the node that contains x. After finding this reference, we allocate a new node and insert it here, writing these two statements of insertion. Now let's see how we can insert at a given position in a list. Suppose we are given a value k and we have to insert a new node at kth position in the list. If value of k is 4, then in this list we have to insert a new node here. The position of the new node will be 4, position of this node will become 5, and position of this node will become 6. So that means we have to insert a new node between these two nodes, and for that we require a reference to this node. So if we have to insert a new node at kth position in the list, we require a reference to k minus 1th node of the list. We have already seen how to find this reference. This code will give us reference to k minus 1th node of the list. After finding this reference, we allocate a new node and insert it here using these two statements of insertion. So now this new node becomes the 4th node, and this becomes the 5th node, and this becomes the 6th node. Now let us see the methods insert after, insert before, and insert at position. This is the method insert after that will insert a new node after the node that contains this value x. So here first we find reference to the node that contains x. After this loop terminates, if p is null, it means that x is not present in the list. Otherwise, p will refer to the node that contains x. And in that case, we allocate a new node and insert it by writing these two statements. Now this is the method insert before, which will insert a new node before the node that contains this value x. And we have seen that in this case, we need a reference to the predecessor of the node that contains x. Now after finding this reference, we allocate a new node and insert it by writing these two statements. Now before doing this, we have put these two checks. If the list is empty, start will be null, and in that case we'll just print this message and return, because in that case we don't want this statement to execute, because p will be null and accessing p link will give us error. Now if x is present in the first node, then we have to insert new node in the beginning of the list. And in that case, start has to be updated. So this case also we have handled separately. Now let's see this method, insert at position. This method will insert a new node at the kth position in the list. And in this case, we have to find a reference to k minus 1th node of the list. Now after finding this reference, we allocate a new node and insert it by writing these two statements. If the node has to be inserted at first position, in that case we have to update the value of start. So this case we have handled separately. Now let's run this program. So this 33 is inserted after this element 3. This 44 is inserted before this element 4. Now we'll insert at a given position. So this 55 is inserted at position 3. We try to insert this 66 at position 16. So it is displaying that you can insert only up to 9th position. In this video, we'll see how to delete a node from a single linked list. These are the different cases that we'll see. Deletion of first node, deletion of the only node, deletion in between the list, and deletion at the end. First, let's see how we can delete the first node of the list. Now, after deletion, this node will become the first node of the list. So, start should refer to this node. So, we'll just write start is equal to start link. And now, this node will not be a part of the list. To delete the only node of the list, we'll just write start is equal to null, and this node will not be a part of the list and the list will become empty. Now let's see how we can delete a node that is in between the list nodes. Suppose we have to delete this node from the list. For that we need a reference to the predecessor node. So we need a reference to this node. Now for deletion of this node, the link part of this node should refer to this node. So we'll just write plink is equal to plink link. So now this node is not a part of the list. Now to delete the last node of the list, we need a reference to the second last node. So we'll just write plink is equal to null. So now this is the last node of the list and this node is not a part of the list now. Now let us see the methods delete first node, delete last node and delete node. This is the method delete first node, which will delete the first node of the list. If the list is empty, we'll just return. Otherwise, we'll make start refer to the second node of the list by writing this statement start equal to start link. Now this is the method delete last node that will delete last node of the list. If the list is empty, we'll just return. If the list has only one node, then we'll make start equal to null and return. Otherwise, we'll find reference to the second last node of the list. So after this loop terminates, P will refer to the second last node of the list and we'll write P link equal to null. And so last node of the list will be deleted. Now this is the method delete node that will delete a node that contains value X. If the list is empty, then we'll just print this message and return. If X is present in the first node, that means we have to delete the first node. So we'll do that by writing this statement start equal to start link and return. Otherwise, we'll find reference to the predecessor of the node that contains X. And then we'll delete that node by writing this statement P link is equal to P link link. Now let's run this program. We delete the first node of the list. The first node has been deleted. Now we delete the last node of the list. Last node has been deleted. Now we delete node 3. Node 3 has been deleted. We tried to delete a node that was not present in the list. So it is showing this message that element 56 is not present in the list.